All right, so my watch is showing 1:33, and it looks like pretty much everybody is back from lunch. So I would like to start this afternoon session. So I hope everyone found a good place for lunch around town or at the Beckman Center. So this afternoon, we're going to be transitioning to a more practical mode. So there's going to be fewer theorems this afternoon, and we're going to talk more about the nuts and bolts of beginning to get running and performing a quantum Monte Carlo calculation. I'm going to give about a 20-minute or so talk outlining the background to the QMCPACK code and the project, some of the features in there, and also how you can go about installing and using the code yourself. Now, we've done all the installations needed for the afternoon workshops, but since obviously one of the goals is that you might continue using this afterwards, we're actually happy to help you get installed back on a home machine, for example, and sitting down with you during the week. And we can write emails to system administrators if that's needed, these sorts of things. All right, so QMCPACK, introduction, features, and a little bit on installing. So very simply, I'm going to give a little bit of a background to the code and the project, some of the main features, how we're organized, how you can communicate with us after this workshop, and also a note about not only building and using QMCPACK, but also validating it. Because if we're going to be a reference method and claim we are more accurate, it's obviously important that we have confidence that the methods are implemented properly and that the code is also correctly installed. Now, I'm going to try and stay away from any particular sort of sales on this and just sort of give a fairly flat presentation. Other QMC codes are available. What about QMCPACK? Well, the history is that it's a high-performance QMC code, and it was originally developed at University of Illinois, later a bit at Oak Ridge, and now by a much wider group. That's the organizers that you see listed of this workshop. I think most importantly for a science research code, it is open source. It means you can get the source for free, and of course it's forkable. So you can go off and do your own branch if you like. There's no obligation to contribute back. We'd appreciate it, of course, but you can do what you like with it. So it's a BSD type license. And I say I try and avoid particular sales, so I'll just note that yes, it is usable for scientific research and competitive publications. We're going to be seeing examples of this throughout the week. And on Friday, hopefully it's not too late, we're going to be showing some current research applications with the code and going into a little bit of the backstory on the calculations. So these are some highlights from calculations on phosphorine, quantum chemical accuracy, chemical accuracy calculations of molecules, some studies of defects in, I think, zinc oxide, a Van der Waals study of some large molecules, and also a study on cuprates, so a transition metal oxide. Very simply, where does one go to find out more information? This is all very simple. We try and link everything off qmcpack.org. That's got the source codes, documentation, and also there are links to the materials and recordings from previous workshops on there. And we'll also, I think, have on YouTube the recordings from this workshop, so you can go back and see what was said and compare with your notes. And if you have ideas for it, if you see anything that's missing, let us know. So what are the main features of this code? Well, as David explained this morning, there's various flavors of quantum Monte Carlo algorithms. And the main ones we're going to be using in this workshop are variational Monte Carlo and diffusion Monte Carlo. There are others. For example, if you want to calculate a property that does not commute with a Hamiltonian, as we'll learn when we learn about projection methods tomorrow, there are other Monte Carlo methods that are of use. We have a wide variety of wave function types, multi-determinants, different Jastrow functions, as we'll learn. We're going to talk a lot about shooter potentials during the week, but this is, of course, also an all-electron method. As with quantum chemistry or DFT, it is, of course, a lot cheaper if you don't include the core electrons. And there are actually additional considerations when one's doing Monte Carlo. You have to take very small time steps for the core electron compared to valence electrons. So there's actually a significant additional saving if you can leave out core electrons. Sometimes, of course, you can't, and you just have to pay. Just same as every other method, right? There is no magic here. If the physics or chemistry demands it, you've got to put them in. One thing that's, I think, of a lot of interest about quantum Monte Carlo methods is that they're applicable to periodic, metallic, and insulating systems just as well as they are to finite systems. So there's a lot of very good methods that work on finite systems in quantum chemical world, but they're not yet extended to metallic systems, for example. And with, of course, QMC, you can use the same method in both places. And this might be useful if you want to land a molecule on a surface, for example. That would be a big calculation, but that's certainly something we would like to do all with the same method to get consistent errors. We are interfaced with two main codes to get input trial wave functions. So for periodic calculations, we use quantum Espresso. We're going to be using this later in the workshop. And for quantum chemical calculations, we're currently interfaced with games. And these are both freely available open source packages. They're all very popular in their own right. One thing I would note is that our inputs are very standard XML and HDF5 formats. So it's actually pretty easy to interface to another code. So if in your research you're already using MolPro, for example, well, we have, in many of these cases, we actually already have a partial converter worked out, or we could work with you to add a converter to, for example, take Hartree-Fock orbitals from your favorite quantum chemistry code. So for example, I didn't mention, I did write Northwest Chem here, but that's something that could be put in. I would note that for quantum chemistry codes, the main work is when one starts considering many multi-configuration type wave functions, because those formats tend not to be very well documented. So we often have to go back and talk to the original developers. That's the real work. If one just needs a single determinant, that's actually pretty easy. But for multi-determinants, normally one has to learn about how symmetry was done, learn sign conventions, and of course it's important to get that correct. We've previously had interfaces to Abinit, for example, and if that needs to be reactivated, that's something we can certainly talk about. Of course, we'd like to have a good reason for doing so, but that's actually a fairly straightforward thing. So if you don't see your favorite code up here, we should talk about it. And I'd also highlight that we also have a workflow tool developed by Jaron Krogel at the back called Nexus. I want to spend a couple of minutes talking about this. There's going to be a lot more later. So this is a workflow tool designed to run many calculations, to stitch them together. Because as you'll have gathered by now, we're going to be doing things like running a DFT code or a quantum chemistry code, and then feeding into, for example, a variational Monte Carlo calculation, and then maybe later a diffusion Monte Carlo calculation. And one can do this by hand, and that's how I did all my calculations on my PhD, for example. But it starts to get pretty laborious. And not only laborious, but it can be error-prone. So we have a lightweight sort of Python-based workflow tool, and this helps automate DFT and quantum Monte Carlo calculations. It can submit jobs locally. It doesn't do global submission to remote machines yet. And this gives you quite a few benefits, some simpler inputs, reproducibility and provenance, and it saves a lot of human time. So a while ago, I did a study in a lot of carbon fullerenes, and that meant doing about 20 calculations on 20 different molecules. And they were all very, very similar and used almost entirely the same computational recipe. And if you have a few different steps for each molecule, suddenly you're doing 100 calculations and you've got to copy files and you want to get out at the weekend, and it can be, you can make a mistake very, very easily there. This lets you avoid it. So one other thing this really addresses actually is this sort of slowness, this hands-on requirement for running QMC calculations. You can also, of course, do DFT calculations this way or any other, and there's other workflow developments. Actually, I should just ask, is anybody here already using a workflow tool, for example, PyMatGen or something like that for DFT calculations? Hands up. So I don't see any, but I would encourage you to look at those if you're in the realm of running many calculations. And I'll note here that this is entirely optional. You are still free to run by hand. So if you want to run old style, and many of us still do, you can do that. But as the study becomes more complicated, obviously the risks go up. And so what you can do is run a network of calculations, and the system will take care of running the different calculations. And when you have some dependency, it will only submit the last job, obviously, when it has all the files there. And so, of course, the advantage is that it's restartable. That's very helpful. So just to get back to QMCPACK, now we've got quite a few developers. And I'd actually highlight here that contributions are welcome. And you can say, so what is a contribution? It doesn't have to be a large slab of code. It could be a note, a little paragraph somewhere in a manual to say a little bit more about a method. It could be an example if you've worked something out from your research that you would think might be useful to somebody. This is all something we're happy to put in, include a citation to your paper or whatever is appropriate, just to make it easier for other people to keep building on your work and using the code. So a contribution doesn't have to be a large thing or a whole new method. We would claim that QMCPACK is fast and efficient. We've obviously done a certain amount of benchmarking, and this is a sensitive, almost religious topic for some people because, I mean, if we think of popular DFT codes, some are certainly more efficient in general than others, but I can always pick a calculation where a different code will win. And if that's your particular research calculation, then you might want to be using, a code that's more specialized for one area or another. So what we would say is, well, we think we are, at least as fast and efficient as other codes. And if you find something that seems to be underperforming compared to what you expect or what you've heard, let us know and we'll talk about it. And if you've actually found a weak point, we will actually go off and improve it, because the grant that is paying for this workshop includes this kind of activity. And we'd love to make it easier for you to do your science as well. So if you find some issue, efficiency, let us know. The rest is, I think, pretty standard for a modern code. It's C++, uses a lot of generic programming to be quite extensible. A lot of effort has been spent to make sure the code can run well on large supercomputers. So it's MPI parallelized, uses threads, which starts to become important for large solid-state calculations to reduce memory usage and also improve the parallel efficiency. And we also have a GPU version, which has limited functionality. So it's only for the spline wave functions, not for Gaussian basis calculations, at least yet. So if that turns out to be something particularly important for you, you should let us know. I've already mentioned standard inputs. And as we're going to hear, I think, a little bit on Wednesday, we have several projects keeping this code up to date for the new supercomputers that are coming down the line. So we're not going to suddenly fall off the supercomputers because when the code is not updated. We have plans to write a reference citation paper later this year, and we're going to acknowledge all previous authors and contributors, so there's still time to make a contribution and get your name on that first one. And as with other codes, we'll probably do a new paper every few years and just add everybody, because we want to recognize every contribution. Now, some more practicalities. Where do you get the source code? Well, there's tarbles available at qmcpack.org. I would note now that actually this is a new thing this last month. All the lab materials are now included in the distribution. So in addition to getting the files on the Blue Gene this afternoon, there's a copy in the main tarball and also in the subversion that I'm going to mention. So you can have them on your own laptop very easily. They do need a little bit of customization to run, but you'll have all the inputs and outputs. Now, there's another way of getting access to the source code, and that's what I call the development source code. Is accessible via subversion, and this is the exact same version that we run day to day. So you can just do a standard subversion checkout, and that gets you access to the complete change history, and it's also the fastest way of getting an update or a small bug fix, for example. So you just do a subversion update. There's a little bit more risk here than using the official releases. So if you're doing production science, I don't recommend switching versions. You pick one and stick with it. I'll explain later about the testing that we do. But for example, if we need to make a quick fix, this is the fastest way of getting it. We can make new releases, of course, as needed if there's a bug fix or an important new feature. I was actually asked earlier about, is the code on GitHub, for example? So, are we using Git or distributed version control? We're using Subversion here. And that's certainly something we're thinking of moving to. We want to gain advantage of the workflow features that come along, often with a lot of distributed version control systems. But we also need to make sure we can tie this into our building and test system and get through firewalls and these sorts of things. So it takes a little bit more thinking, but we certainly plan to go in that direction. If that's a big problem for somebody, let us know, and that could encourage us to move sooner. But right now, this is a very quick way of getting the source code. What do you do if there's an issue? Well, we have an open access, or readable at least, Google Groups website. So if you Google QMCPACK group, you'll find this page. It's fairly low traffic, and it is moderated. So the first time you post, someone here has to click and say, this is not a robot. This is just to keep spam off the system, which Google is not yet perfect at. They need to work on their AI a little bit longer. And actually, we prefer postings here to email because it lets other people see that there's a problem and that you've got a question. And also, we hope, of course, to have an answer there, so some workaround or a note about when the update is going to be. So this is good to see. And so it's also nice to learn about any successes as well as any troubles. So I'd be very happy if there were more postings there. OK, so you've been talking for 20 minutes, but I'm going to run a bit longer. So now I'd like to switch and say a little bit about how to build QMCPACK. As I said earlier, it's not necessary to build QMCPACK for this workshop. It's all built and sitting waiting for you, as we'll see later on this session. But you're welcome to have a try on maybe a Linux box you have at your home institution, or if you have a Linux laptop, actually, it should be pretty straightforward. And what I'm now going to do is talk through a little bit that's taken from actually chapter 2 of the manual. We have a new PDF manual, which is linked. And I'll note that we have some older HTML documentation that's still on the website. And these cover slightly different subsets of functionality. But we're bringing everything into this manual. And so you want to definitely start here with the PDF, particularly for the install section, because that is absolutely up to date. So what do you need? And these are all fairly standard things. If you're used to installing packages, this should be pretty straightforward. You can talk to your local system administrator if you need any help. We need a C++ compiler. We use CMake to build. MPI, I've already mentioned, Lars LAPACK. And then we use libxml, HDF5IO, Boost, C++ class libraries, and also FFTW. And this is all free software that's in all the standard package managers. So if you're on Linux, for example, so if you're sitting on a fairly standard Linux machine, you won't have to build any of this. So actually, my recommendation is if you're interested in building, is get hold of a modern install of Linux on a laptop or an up-to-date workstation, and try installing there. Because that should give you the easiest time of it, and you'll learn what the install process looks like for when you go to a more exotic machine. And we actually have instructions for quite a few combinations of Linux machines and OS X as well in the manual, and so I recommend following those. What does it look like? Well, here I'm going to give an example. I'm going to check out the source code. We have to get into the source code. We're going to make a build directory. And then we're going to run CMake. And CMake is so-called out-of-source compilation. So you can have multiple builds sitting alongside the source files. And this is actually how I normally build the code. So this is what I type on a pretty regular basis. And all I'm doing here is specifying the exact name of the C compiler and the C++ compiler with the MPI wrappers. And we do attempt to auto-detect this, but the danger is on many systems you've got many different compilers available in different wrappers, and the auto-detect system might pick up not the version you want. So it's much safer to specify the version you want, and then you know there's going to be no issues. I would note here, this ... at the end is very important because it refers to where the CMake list file is that CMake needs. And then you can do a parallel parallel build, make minus J16, and QMCPACK will build in 2 or 3 minutes. It's actually pretty fast on a modern system. There's other examples in the manual. And just to give my impression, this is very subjective. I build a lot of DFT and classical MD codes. And I would say we may have a few dependencies that other codes don't have, but the actual installation process is similar or easier. So on the whole, it's pretty similar to an electronic structure package. There's lots of environment variables you can set up in the examples. As are explained in the manual, if libraries are installed in a strange location, that's all pretty standard for these packages. So this example, actually, I just cut out of the manual directly. So here, the locations are pretty standard, but if you're on a departmental workstation, for example, there may be somewhere odd. Now, an important topic, which is how to validate the code and have confidence that it's working correctly. So we've actually put quite a bit of effort on this, and we actually have a test system included with the code, and we actually highly recommend running this. These tests can show up problems. I mean, we may think we may have bugs in the code, but more frequently, actually, it shows up some issues with the libraries that have been used. Maybe some incompatible versions got picked up, and this will help identify that. So what do? We run, in our test system, we run QMCPACK many different ways, and we test against known good results. So if we take a single determinant wave function and then do variational Monte Carlo, as David was explaining, that would actually be equivalent to doing a Hartree-Fock calculation if we had Hartree-Fock orbitals. So if we feed in Hartree-Fock orbitals, we can actually check that we get exactly the same result as a Hartree-Fock code, for example. And so there's various tests like that that are in there to make sure everything's consistent. How do you run this? We run a program called ctest, and we have a set of tests which is a prefix named short. Those will be quick running tests. And so if you type ctest minus r short, it will run 30, 40 or so tests. And it takes only a few minutes on a 16-processor machine, so this isn't much burden. And if all of these pass, you should have a lot of confidence that everything's working well. There's actually a more thorough test set. We run these weekly. That takes a number of hours to run through, and that's also worth doing on a regular basis. In future, actually, we're going to be adding whole workflow testing to this just to have confidence. Just to have a note here, we actually test the code nightly on many different machines. We have a sort of a dashboard. This isn't public yet, although we're going to try and find a way to make it public. And this is just to give us confidence that nothing has slipped through. And really, all codes we use should be doing this. So for example, the Abinit project has had a build bot for a long while. Some other electronic structure codes don't yet have this, and I think it's very important for science actually that we can have more confidence in our results and our publications. Finally, just a note about building a quantum espresso. We have to convert the output of quantum espresso to a format that we can read, and quantum espresso uses its own sort of internal save format, which is varying between different versions. So we have a small script which will download and patch specific versions of Quantum Espresso for you. And what that does is it adds a utility, a post-processing utility called PW to QMCPACK, and it also adds HDF5 support. So there's a README on this, and to configure Quantum Espresso after it's been patched, you just run the configure as normal, and you add dash with HDF5 and give it the HDF5 directory. If you don't do this, you may still get a PW to QMCPACK executable, but when you try and run it, it'll say no HDF5, can't help you. This is a step that we'd like to get rid of in time, and so we are trying to encourage the Quantum Espresso developers, which we're in contact with, to add HDF5 support directly into Quantum Espresso. This has been, many people have been requesting this, but of course it requires someone to go in. It also requires them to agree to support this long term. But that would be helpful for many codes interfacing with Quantum Espresso. So for example, the GW people would also be able to make use of this. So that was my last slide. So just to summarize, QMCPACK is a full-featured QMC code. You can use it for production science. Look at qmcpack.org. And I'd note here that the improvements in the code or the features, documentation, are driven based on sort of the needs that we perceive and also what we hear from people. So let us know, either directly or on the Google group, if there's something that you think should be improved, if you had a hard time running something, for example, if you have a suggestion for improvement. And I just encourage everyone to be very vocal on that. So, any questions? Simple.
How about pseudopotential library?
Okay, very good point. So we're going to be discussing pseudopotentials later during the week. In terms of a library that is using pseudopotentials that have already been developed, we now actually include in the distribution a set of the Burkatsky-Philippi-Dolg Hartree-Fock potentials in games format and also converted for Quantum Espresso. We would note that because they weren't developed for Quantum Espresso, it's important to do some extra tests. We have to regenerate the projectors that are used in the DFT, and there can be a little bit of risk there. We have some fair confidence, but we haven't done a full study of that. And we plan to add other sets, actually. So for example, Jaron Krogel had a paper fairly recently on 3D pseudopotentials, and those will go on in there, and we'll include links to the papers where validation studies were done, because same as with DFT or an effective core potential for quantum chemistry, you need the validation data as well, and ideally on a system as close to the one that you're going to be doing your calculations on. And actually, if people have, as other researchers publish pseudopotential sets, we'll add them as best we can.